Perfect. Okay, I guess we're ready to start. My name's Paul Steciuk with a company called NEPSI, NEPSI, Northeast Power Systems, Inc. Contact information. Thank you to Bechtel for hosting, and thank you for IEEE for allowing me to present. So today's presentation is harmonic analysis. Knowing the basics is essential. Okay, that's in a nutshell what we're doing. So just a little bit about my background. I'm a co-owner of this company called NEPSI. We started 25 years ago. Our primary product is metal enclosed capacitor banks, harmonic filter banks, between the 2.4 kV and 38 kV level. So that's where my level of expertise is. Harmonic analysis is one of those. I did harmonic analysis at a company called Power Technologies, Inc., and also at another company called Qualtech Engineers out of Pittsburgh. So I did maybe 8 years of analysis type work before I started this company with two brothers in 1995. So key product offering is cap banks, filter banks, and that is why this presentation is about harmonics, because it's one of the only things I kind of know, reactive compensation at the medium voltage level. So we do provide harmonic analysis and things like that as a company. Oftentimes we leave that to the consulting firms to do, but having this core knowledge is important because it allows us to properly design and rate the equipment. And we do have smaller projects that come in where an EPC is not involved. They need some type of analysis work. We'll do that analysis. So we use a program called EasyPower, and that's an ESA software package, and it does harmonic analysis. But there's ETAP, there's SKM. They all do a harmonic analysis. They all use the same principle for their analysis purpose, the algorithms that are used inside. So this is the type of equipment we build, is harmonic filters. So today we're going to talk about harmonic analysis and to some degree harmonic filters. Okay. So this is an example of something that we shipped into South America. It's a very large harmonic filter, 25 kV. It's 200 kV BIL because it's up at I don't know, maybe 14,000 feet. So there's an altitude derating issue, and that's what it is over there at the end. So mine projects tend to have a lot of harmonics because they're using cycle converters, OCI drives, VFDs, all kinds of stuff for the grinding mills. So they use very large harmonic filters. Here in Houston, you're doing LNG projects, and you have also a lot of harmonics you're dealing with there, pump stations, things like that. So the first thing is, why do a harmonic analysis? And normally, if you're installing a very large drive, you're trying to determine compliance. You want to know if you comply with IEEE 519, or do you comply with a utility interconnect requirement? So this is something that you would be concerned about. 519 is a point of common coupling issue, right? The point of common coupling being on the primary of the interconnect. Okay, we're typically maybe 138 kV voltage level if you're in a large plant. Okay, so it'll be a sub-transmission or transmission level. But it can be even down lower. It might be down to 13.8 level if you're a smaller plant. So that changes. But you're meeting some kind of current distortion limit there. Within the plant, you're concerned about voltage distortion. Right? You're installing a large drive in the plant, and you're concerned about voltage distortion. It's very important to calculate voltage distortion throughout a plant because it's voltage that impacts all the other equipment in the plant. So that is concerned about current distortion within the plant environment because the current's just flowing in the conductor. It's not causing anything. Maybe a small amount of additional heating, but I could tell you the additional heating is very minimal. Okay, you have transformer issues kind of down in the lower voltage network that you have K-factor transformers and things like that. Yes, you're concerned about that. But once it's into the network, harmonics is not really a major concern on those devices from a current standpoint. But voltage is a power quality concern, and that's something that you're looking to calculate when you do analysis. So the other thing is you want to evaluate resonance concerns when you do harmonic analysis. If you're adding a capacitor bank, you have to have a concern for harmonic resonance. Whenever you add capacitor, you're adding resonance to the network. Every time you add a new capacitor bank, you're adding a new resonant point. So in a system that might consist of multiple impedances with capacitor banks, I say at the low voltage and medium voltage network, and then some scattered throughout the transmission network, you're adding a bump in your impedance sand, and another resonant point. So you do harmonic analysis to evaluate those resonance concerns, and the reason you do that is because resonance causes problems, and we'll show why in this presentation. You also have resonance concerns from cables, cable capacitance, an issue that's common in the wind farm industry. Just the cable capacitance alone can cause a resonance concern. So you're doing a harmonic analysis for that reason. And then finally, if there is some type of harmonic problem, you want to evaluate your filter design. So that's the reason you're doing it. So here I'm just going to briefly talk about harmonics, what they are, okay? On the top waveform here, we have a linear load. And a linear load means that if we apply a 60 hertz voltage, you get a 60 hertz current. So we're not, the current waveform matches the voltage waveform, so it's a linear load. On the bottom here, you have nonlinear load. We put the blue curve in, a voltage waveform, and you get a square wave. It would be similar to some kind of power converter, power electronic type device. Okay, it's allowing a square wave of current to flow for the application of a sinusoidal voltage. Okay, so through Fourier analysis, you can take that square wave, if it's periodic in nature, which would be the case for a continuous run type load, and you can break that down into subcomponents called harmonics that are multiples of the 60 hertz. So second harmonic being 2 times 60, third harmonic being 3 times 60, or 3 times 60 hertz, 180 hertz, and so on. So to some degree, what matters is that you're concerned about the current, okay? You don't really need to know how this power electronic device works to do harmonic analysis. What you need to know is what harmonic current does this device put out? What's the signature of that device? 6-post drive is going to put out 5th, 7th, 11th, 13th harmonic, and it's going to put out currents, the 5th as 1/5 times the fundamental, the 7th will be 1/7 times the fundamental current rating of the device, and this is roughly speaking, right? But each of these devices has a signature related to it, okay? And that's your concern. So when you do a harmonic analysis, the first question to the supplier of the drive is, what is the harmonic current output of the device? Okay, and that's really your concern from an analysis standpoint is, what is it? The output current from these devices, most of them are modeled in the programs as ideal current sources. It's an ideal current source, which means that if it's, say, a 5th harmonic and it's got a 20 amp current injection, it means it's going to put out 20 amps. If I double the impedance of the source, it's still going to put out 20 amps. Kind of acts like a CT. No matter what burden impedance you put on the secondary, right, you still get the same current flow for the most part, right? Which is really the fundamental understanding that those current sources are what is creating voltage in the network. We talked about impacts already. I kind of have the slide in there and I skip over it every time, so it shouldn't be in there. Because I always cover it before I get to it. So the process of doing a harmonic analysis, and this is kind of a table of everything that happens during the harmonic analysis process, but you got to create a model. For the most part, the model is getting developed along the process. SKM and ETAP and all these programs, you're doing load flow analysis, short circuit analysis, maybe arc flash, and then harmonic analysis is also in there. So you already modeled all the impedances in the network, and that's what the harmonic analysis model requires. But it requires just one additional piece of data, and that's the harmonic injection data, right? You've already added capacitors in there for your load flow, so you know your reactive power requirements. But harmonic injection is really the thing you're adding. So some programs allow you to add up all the harmonic current in the network, and you can do it in Excel, come up with a total, and make that your current injection on the bus bars. You just sum it all up as in one equivalent. That's the simplest way. It's the way I like to do it. I just add everything up. I do some kind of load study and say, okay, where are my large VFD drives? Add all those up. Based upon the signatures, I have a total. When I'm adding those up assuming that the phase angles are always the same. This is a key concept here. The reality in the real world is those phase angles are not lined up at all. A fifth harmonic, one VFD drive, will not line up with the fifth harmonic from another VFD drive. They're phase shift from each other. So the worst case is to assume they all add up together. But in the real world, they're not added up. So your harmonic analysis is a pessimistic result. I mean, it's going to give you a result that is worse than the real world. So that's one of the things to note, that it tends to be that if you calculate, whatever you calculate in your analysis, a lot of times is worse than what you're going to get once you start to plan up. So if you have a system that's working in your model, chances are it's going to be better when you do when you build a system and you actually operate it. So once you develop this model, you validate it. The validation process, in my opinion, is I always do a short circuit. I fault the bus and I look at it. Do I have some reasonable level of fault current? You know, a 13.8 bus, I'm going to be looking for 10,000 amps, 5,000 amps, 20,000. Just check it. Does it make sense? Same with low flow, run to low flow. Does everything make sense? Okay, if it does, you validated your model for the most part. There is an occasion where somebody might go out and take measurements, okay, harmonic measurements, and you could take your harmonic injection data and put it into the model and compare that to your measurements. And I see that, and I used to try to do that, and that's opening really a can of worms, because when you try to match your analysis, okay, what you put into your analysis to your measurements. So what I'm saying is somebody went out and took harmonic current measurements, they put that harmonic current measurement into their data file, and then they run the simulation and they calculate a corresponding voltage at the bus, the corresponding voltage distortion at the bus. So you got some value of fifth, some value of seventh, some value of 11th. They do that, okay, then you compare it to your study. You compare the study to the real world. It's very difficult to get those to match up. So I tend to try to stay away from doing that. I've never, you've taken a study that might take a week to change weeks or 3 weeks, because you're going to be something wrong. I'm going to start fooling around with impedances, and it's difficult, very difficult. So I say don't do it. And it doesn't matter in the end, really. After you do that, you do impedance scan analysis. We're going to talk about impedance scans and what they mean and how to interpret them, the things I look for when I do a study. So we'll talk about that. I think you'll have a real good understanding of the impedance scans. When you get a harmonic study from somebody, okay, a lot of times, if it's a big project, you're going to have 30, 40, 50, 100 different impedance scans. And I find that that's difficult to read those reports in the end. I'd like the executive summary, what the engineer has found. He might notify of certain conditions in the plant that you have to watch out for. But in my opinion, when you get these studies and they're really thick and they contain all these impedance scans, it's almost a waste of time. It's only important to the guy who's actually doing the study. So you calculate voltage and current distortion. Okay, so you have impedance scans, and then you're calculating voltage and current distortion in the plant. And that's really one of the prime outputs of these devices. And then you're checking for 519 compliance. Okay, do you meet 519 compliance? Filter design. So say you do your analysis, you got a problem, right? You can do a filter design. The filter design process is, for us, it's to actually use a spreadsheet tool. We have a spreadsheet tool on our website for designing notch filters, C-high pass filters, high pass filters. That's the 3 types of filters that are used. Normally, most consulting firms are using some type of analysis spreadsheet tool. And it's a very simple calculation. I have an example one at the end here for a notch filter. And for C high pass and high pass filters, it's very similar. You can go to our website and get that spreadsheet. If you email me and you want the password to the spreadsheet, I'll give it to you. I got no problem giving it out. That way you can go in there and edit it and make it your own. You can understand what's going on. In the end, you need to trust the tool you use, and that's the purpose. We don't mind sharing that tool. Somebody gave it to me 15 years ago. We grew it to do all kinds of things that we cared about, but you might have something else you care about, so you can add it to this spreadsheet tool and grow it. I don't mind. And then this report. And report is where most of the time is spent when you do harmonic analysis, is in that report. Writing it, getting the grammar correct, all your spelling, all that stuff, and all your graphs, and labeling it, and numbering them, and all that takes a lot of time. So in my opinion, I always like to try to shrink the report to an executive summary, and then do a presentation after. In other words, meet with your client and talk about what is the issue with the program up and running. A lot of these programs are click, get an impedance scan. So you can explain to your client, hey, this is what's going on, and this is why I put a filter in, and see what happens. Because in the end, most clients are not going to be able to read that report and understand it anyways. So somebody needs to explain it to them. So I say try to save the money and cut down on the report. So we call it a letter report. And it's basically just an executive summary. And then we say we'll do a presentation. And that's through a WebEx. So very cost effective. We can do, I say we do a $30,000 study for nothing almost, because we don't have to write this detailed report. That's the difference. That detailed report can be very time consuming. So we're going to get into building from here. So this is a very simple system, and I got this thing. You got to check this out. I haven't showed it. Oh, wait a second. Look at that, huh? Have you seen this? Anybody seen this yet? So we have, this is pretty cool. I bought this the other day. So you have this source equivalent here, okay? 10 Ka, it's a 7.5 Ka X over R 13, 138 kV through a service transformer down to 13.8 kV, and we have a harmonic current source there. So here's 3 megawatts, 3 megabars. So we come up with, that's like a rectifier, would be equivalent to like a 13.8 rectifier that's running at about 0.7 power factor, which is pretty typical. So that's what we did here. You could have taken the whole plant, add up all the harmonic currents on that 13.8 kV bus and summed it up here. That's what you could have done. With ETAP, you might include a harmonics within each and every device in the plant, and that's another common approach to doing harmonic analysis. But in either case, what's really going on is you have this current source over here. It's kind of funny. Over here, you have this current source, right? And you can see I labeled I5 equal to 8.3, I7 equal to 6, I11 equal to 3.8. They are harmonic current injections. That's the ideal current source. And in fact, we kind of labeled it as an ideal current source here. And so what this means is that at the fifth harmonic, 5 times 60, right, 300 hertz, I'm injecting a current of 8.3 amps, and it's flowing into this impedance. So the equivalent circuit there is source impedance followed by transformer impedance down below, and then you have your current injection here. So that's the very simple model. And if you think about this, if you want to know the voltage here at the 13.8 kV bus, that's what this is. It's just, and you want to know the fifth harmonic voltage, it's 8.3 amps times that impedance. That's it. And that's the fifth harmonic voltage at that bus. If you want to know the fifth harmonic voltage here, okay, it's just that harmonic current times that impedance there. And that's your line to neutral voltage distortion at the fifth harmonic. You got to do the same for every harmonic. So that's the thing. 60 hertz, you're doing a low flow analysis. It's one frequency. Harmonic analysis, you have to do it at every frequency. So it can be pretty time consuming to do it on paper. But I'm saying I'm telling you, if you have a program and you really want to know that the program is doing what you think it's doing, you have to model a system like this. Because in the end, how do you really know what the program's doing? And I'll give you, I think like ETAP, when you put in the filter parameters, it wants to know single phase kVAR for the filter. For EasyPower, it wants 3-phase kVAR. It's not immediately clear when you pull up the window in there and you type in the values, what to enter. So in the end, you have to do some type of validation to validate that, okay, because you can see the calculation here is easy. You can do this very easily within any analysis program and do just a simple current injection, even if it's 1 amp at every frequency. Do your analysis and say, does it make sense what I'm getting? So that's kind of the purpose of this, is to allow you to go back to your and then understand what it's doing. So I assigned impedance values to that model. You have here 0.1 amps of the source impedance, and I'm using 0.1 ohms, sorry, 0.1 ohms on the source impedance, 1.42 ohms for the transformer impedance, and that's X of L. Okay, that's the reactance of the transformer, the reactance of the overhead line. The key point here is that this value here is very small. It's dominated by the transformer impedance, right? It's very dominant. The other thing is the value of ohms is 0.07. The resistance is very low. Same with here, very low, 0.01. So you could technically toss the resistance out for a very simple analysis and just do the analysis with X of L, especially in a model like this. So the voltage at the fifth would be 8.3 times 1.42, but then times 5, because I'm at the fifth harmonic. The impedance of the impedance, and I don't have it written here, is equal to 2 pi FL. 2 pi FL is equal to X of L. So F is in the equation when you have an inductive component. Inductive component is J omega L, 2 pi FL. So if I have 5 times the frequency, I have 5 times the impedance. And then at 7, it's 7 times the impedance. So that's all you really need to know. You calculate your fundamental inductance or inductive reactance, multiply by 5, 7, 11, 13. You can calculate your voltage distortions at each one of those values. So when we're all said and done, we can take those impedances and combine them into one. We add the R's, we add the X's separate because it's a phasor type quantity, complex impedance, right? So you can't add the R's and X's, they're separate. So we have the 1.52 as the X component at 0.08 ohms. So it's a very simple series circuit when we're all said and done. If you calculate the impedance at every frequency, okay, and we got harmonic number down here, not frequency. Sometimes you're going to see hertz on this axis, not harmonic number. I prefer harmonic number. But sometimes it might say 300 here instead, to say 300 hertz. Okay, but at the fifth harmonic here, okay, I'm reading about 7.5 ohms, which means if this was actually 1, if that was 1 amp at the fifth, I would take 1 amp at the fifth times the value I read off this chart is 7.5. I would get 7.5 volts line to neutral. That would be my voltage distortion, line to neutral at the fifth. I could do the same at the 7th, same at the 11th, do the same thing each and every time. From there, you can calculate this VTHD number, right, here. VTHD, just take the sum of the square root, realizing that V1, again, is line to neutral, not line to line, because what we've done is we've taken, and we noted this today, we've taken a 3-phase network and we converted it to a single-phase network. So a single-phase network assumes that everything is balanced. We're using 3-phase current injection, and our impedances of the network are all balanced. And right, the power systems 101, you can take a 3-phase circuit and convert it to a single-phase circuit and simplify the analysis, and that's what this is doing. So you can do the same thing with ITD, the total demand distortion. In that case, this I1 is demand current, but it could be the instantaneous current. In that case, it would be it would be just the I1 network. And then again, sum of the squares, square root gives you ETHD, ITHD, or ITD. And that's the premise behind here. So we use this curve. This is a good reference line to keep track of, and I'm going to continue to use this because this is dominated by the source impedance and the transform impedance, and really the transform impedance dominates that impedance profile. And so you can see that at some point you can inject current at the 5th, 7th, 11th, and you will reach of ETHD at 5%. At some point, you're going to get there. What level of current will it take at 5th? And you could do the calculation. How many amps at the 5th would it take before I got to 5% VTHD? And you could back into that value real quick. So sometimes I have a customer who will say, I have X number of 6-post drives. I can take that value and say, well, what's your current? Right in the calculator. I'll do it on the phone with somebody. I'll say, well, what's your total horsepower connected? I can calculate the total 5th. What's your transform impedance? And within 30 seconds, I've already calculated what your 5th harmonic current, harmonic voltage will be from that drive load. Very simple, without even opening a program. So it's almost as simple as doing a simple calculation for a short circuit on a secondary bus. You can do the same here if you just know this basic principle. So this is funny. This is something I didn't do today, but we have questions. I forgot about this. I did this for Engineers Week up in New York, this presentation. So it's a question. You guys can look at it for a second and think about it. If the network short circuit current goes up, what would you expect the voltage distortion to do? So the short circuit current goes up, which means what? It means the impedance of the network has gone down. So the voltage distortion would go down, right? Less impedance. So and you're just injecting same amount of current, but the impedance has gone down, voltage distortion has gone down. So that's the premise behind that question. It's an important point. Weak systems for the same VFD drive is going to produce higher distortion, voltage distortion on a network. Got 4 more questions. I had to do 5. New York State requires 5 questions to get a credit, a continuing ed credit. So, so it's more difficult to get those credits in New York. So you can't just give out a certificate. I had to send mine in for approval. So I sent it in. Okay, so now we add a capacitor to the network. So the capacitor follows this green curve. You get the red curve, but the green curve, X of C, the capacitive reactance of a capacitor, and I calculated here for 1 megavar is 190. At the 5th harmonic, I would have to divide by 5 because it's 1 over J omega L equals X of C. So you have your capacitor. You can calculate X of C at the fundamental is kV squared, line to line, divided by the megavars. You have your value of X of C. At the 5th harmonic, I would divide by 5. At the 7th, I would divide by 7, and so on. So I can get this impedance curve here. At higher frequencies, the impedance is dropping off, so I get this asymptotically decreasing curve. There is a point where this is equal to that, and that's this crossover point here, right? And that equals the famous formula, where is it? Here, X of C divided by X of L square root. And you see that all the time. And it's a key formula to pay attention to, because whenever you're adding capacitors, you should be trying to mentally think, okay, where's my resonant point? Okay, is it at the 5th? Is it at the 7th? Is it at the 13th, 23rd? Is it at a point where I want to be nervous? So remember I said that drives have characteristic harmonic spectrum. So your question in your mind should be, where is this resonance occurring? And do I want to be concerned? Once you get down to the 11th, you're kind of, I think you're sunk, in my opinion, because there's 5th, 7th, 11th, 13th harmonics. You're kind of sunk. You're going to have to do something. You're going to have to be concerned about resonance. But at higher frequencies, there's sometimes bigger gaps, and you don't have to be as worried about it. Anyways, we're going to talk about those worries in a second. Any questions for anybody? Okay, So if I were to go back to the slide, and if I were to look into the network from there and calculate the impedance, it's the power over sum, right? That's the rule. It's a parallel circuit. You got this in parallel with that. So it's a power over sum rule that you can apply. You have to make sure that when you're doing this power over sum rule that it's a complex quantity. You have to pay attention to this complex quantity issue. So you got to do power over sum. You have to be taking care that you have a complex number. So it's not 100% straightforward, but this can be done very easily in Excel if you take a little time, and I've done this in Excel too. So you get this magenta curve. This blue line here represents the impedance of the transformer, right? That same impedance curve. So you can see that for a current injection, we are dealing with a much larger impedance now, right? At all these frequencies, we got this huge frequency. We've gone from values that were, remember, 7.5 ohms at the fifth to being something on the order of 400 to 500 ohms potentially at the fifth. It can be very significant. So 500 ohms times 1 amp. Now, I only had 1 amp. Before you said 7.5 volts, whippity-doo. Now it's 1 amp times potentially 500. You got 500 volts, which represents a huge voltage distortion. It'd be 500 divided by, in this case, 13.8, so 7.96 kV, 7960. So 500 divided by 7960 would be your voltage distortion for just 1 amp of current injection. So that's why I say you always have to be concerned about resonance, because if you have resonance, when you add a capacitor bank, you got a potential for a big problem, even for very low-level harmonics. In this regard, when you purchase a high-pulse drive, the premise behind buying that high-pulse drive is that you don't want 5th and 7th harmonic current. You might not want 11th and 13th. Maybe you bought a 24-pulse drive, and technically speaking, theoretically speaking, right, you wouldn't have 5th, 7th, 11th, 13th harmonics. Your first harmonic would be 23rd, right? Plus minus 1 is the formula for figuring out that harmonic. So 24 n plus minus 1, so you'd have 23rd and 25th. But the reality is that all those drives will put out a low-level 5th, 7th, 11th, 13th, even if it's a 24-pulse drive, because the network's not perfect. You have unbalances in the network, and you're going to get a small level of current injection. Additionally, you're going to have other loads within an industrial plant that will put out low-level 5th, 7th, 11th, 13th. So even if that drive was as perfect as the manufacturer said it was, it's still going to put out some 5th, 7th, and 11th, because the drive's not perfect, it's not doing everything perfect, and the network impedances are not balanced. So in a theoretical basis, with an analysis tool, you could say that it's perfect and it's not putting out harmonic current, but it is. So 1 amp of injection at the fifth can be a problem, and that's really a key point to take away from this. I'll make note of it too. The peak here, that peak is determined by this formula here, right here, x of c squared divided by n, which is the frequency by which the resonance occurs, divided by the impedance, the resistance of the network. So you think about R in a network is a very small number. The resistance of a network is very small, and that's why you get this big peak, because you got x of c squared divided by n divided by R, and R is very small. The other thing about R in the network is it's an unknown quantity. It's not easy to quantify. The nameplate rating of the transformer does not contain the resistance of the transformer, so it's a value that's already difficult to quantify. And resistance is impacted by frequency, skin effect, proximity effects. So you may be able to say you know the resistance, but only to a degree do you know the resistance of the network. So the magnitude of this peak becomes a question. Okay, you can easily be off by a factor of 2, easily. It could be, this could be 300 ohms, or it might be 600 ohms. It could easily change. So bear that in mind when you do have resonance. you have a temptation to say, well, what is my harmonic current injection at that point, and can I handle it? Because that value might be double than what you think. So it's something to consider, that you don't really know that number very well. Okay, so we're on to parallel series resonance. So I got the same exact network, and if you stand at this point and you look into the network, you have both a series and a parallel resonance, right? You can see that there's a resonance here, and then there's a parallel resonance here. So you have the parallel resonance here, and here you have a series resonance. So coming from this point here, you can see I have X of L at some point will equal X of C there. And I would have a very low value, that would be this. But then I also have a parallel resonance. So depending upon where you are, you can have parallel and series resonance. For the most part, that doesn't really matter too much, this resonant point from this location. But what you often see is when you have low voltage capacitors, 480 volt, and I'm on a medium voltage network, okay, this might be a low voltage capacitor bank. This might be a step down transformer from 13.8 down to 480. You have this series resonance. Not series, it's a series resonance, but technically it's a series resonance where it results in a low impedance. So it becomes a sink to harmonics for a medium voltage drive. So if you have a large medium voltage drive, it might flow back towards the low voltage network and fail those capacitors, because the low voltage capacitor will not necessarily be able to handle that harmonic current. Okay, so the reason I bring this up is when you have a network, every time you add a capacitor, you add complexity. If you have a medium voltage network, a low voltage network, and then say a transmission network, and you add capacitors at each one of those levels, you're creating more complexity in your impedance scan. And it makes it more difficult to design that system and to check that system. So I say do power factor correction at one voltage level. Pick your voltage level and do it all there. That would be a preference. Do it at that location. For us, we would recommend medium voltage. It's a good place for it. Low voltage, you can't get the megabars you need. It takes too much. At medium voltage level, it comes in at a lower cost and less stages, less complexity, less current. At transmission levels, you got to switch this, and that comes very expensive too. And plus, you're closely coupled with the transmission network, which is owned by the utility, and they have their own thing they're doing. You have other customers local to you that might be adding capacitor banks. You might be trying to put a filter in, so it makes things complicated. So a medium voltage network is a good place to add reactive compensation, whether it's capacitor banks or harmonic filter banks. Question 2. There's 2 questions. So when correcting power factor in a system, what concerns do you have? Okay, number 2 was, what does the resonant point change? How does the point change with increasing capacitance, reactive power? So if we go back to this one here, that the first concern when adding capacitors, of course, resonance is your concern. What are the resonant points? And then finally, if you add more capacitors, it's to shift this curve to the left. It's shifting it to the left. You're adding more capacitors, and that's the general rules. The more you add, the more it shifts to the left. Key point, when you do power factor correction, it tends to be that networks have a certain impedance, and by the time you get done correcting power factor, you're going to end up with a resonance between the 5th and, say, the 8th. You're going to find that your resonant point is going to come down to there. If you have a requirement to correct power factor to near unity, invariably the resonant point comes down to that lower frequency, and it becomes a concern. What about tuning around resonance? This is a common theme you hear from some people. I got the formula. I calculate 5.59 for harmonics resonance, and they say, okay, I have a problem. I'm not at the 5th. I'm not at the 7th. I'm right between the 5th and the 7th. Everything is good. But you can see here, this is our reference line. That's what it was before. And you can see at the fifth, come up, I'm maybe at 20 to 25 ohms. Okay, so there's a certain width to this resonance. Okay, and you're not directly on resonance, but you still have increased the impedance of the network from this base value, what I would say 7.5 ohms, to some higher value, say 20 to 25 ohms. The next question really is, how accurately do you know this? And that's what we get into. How it's going to move, it can move around, right? When a utility calls and tells you their short circuit level, right? How much can you trust that utility's level of short circuit current they gave you? And one of a good point is if you live in Kentucky where there was a lot of coal generation, right? The old administration comes in, they shut those power plants down, short circuit level changes in that area. So you can't trust that the short circuit level is going to stay the same. Depending upon what power plants are running, the short circuit level changes. That change in impedance shifts this around a little bit. So today it might work, tomorrow it might not. So it's not a good practice to say you can tune around resonance, because it will not work that well. And I kind of shaded in the areas. So the purple red represents areas of increased impedance, which means you added a capacitor and the result was increased voltage distortion because it added impedance to the network. But for harmonics above the, say, the 8th harmonic, the impedance has dropped off, and we've actually reduced voltage distortion for that same current injection. So it's an interesting thing. And we once upon a time built one bank where we've increased the rating of the cap bank to bring that resonant point all the way down below the 5th, and we kind of capitalized on this green area. But we've only done that once, so it's not very common. But something that you can always consider is if you got a resonance around a 5th, maybe you want to just add some more megavars, shift it more to the left, and go with that and not install a filter. And the reason is that filters are more expensive. You're paying for a filter bank more, maybe double the price of it than the price of a cap bank. So think about that. So third question, is it possible to tune around resonance? I think the answer is no. I think I've talked about that. I think hopefully you agree with me on that. If attempting to tune around resonance, what concerns would you have? I think the answer is things are going to move around. Your short circuit impedance will change in the network. So tuning around resonance is not always applicable. We had another project where when the tap changer changed on the main, there was a small change in impedance of the transformer. And they went from being acceptable to not being acceptable voltage distortion within the plant. It was a big plant, and whenever the tap changer went to a certain location, it was enough impedance shift that it caused the resonance to be a major concern. Okay, so there was a whole effort to map out the impedance of this tap changer and to operate the tap changer within a range that it wouldn't cause resonance. But this was after everything was purchased, and that's typically when you get people talking about tuning around resonances after they purchased the equipment. How can I make this thing run? Because nobody wants to say they screwed up or they made a mistake. They just want to make the thing work after, and that's the reality of what happens.
Was that on a de-energized tap changer?
It was a LTC.
Low tap.
Yeah. And it was a big plant, so the thing wanted to move. It was a big plant. From no load to full load, it wanted to move. So here we have a multi-stage capacitor bank. And this is common, right? Industrial plants want to regulate power factor to 0.98 or some value close to that. So as the load comes up, you're adding capacitors, 1 megavar, then 2, 3, and 4. And so basically you get a range of resonances, right? And so in this case, I have a resonance maybe near the 13th, and then it drops down to say the 8th, and then down to the 7th, and down to almost 5.59 for that last one. So you get a shift in resonance, which means that if you're installing power factor correction and it's automatic banks, you've increased your odds of having a problem, really, is what you've done. And you have resonance concerns at each one of those locations. Your study must account for each operating condition. So if you have a 4-stage bank, I need to do the study for each of the 4 stages. If I have a main tie main, I need to do the study with the tie closed. I need to do a study with the tie open because I have a different source impedance, right? So now you have more, right? More simulations. And this is the thing with harmonic analysis. A lot of times you end up with 30, 40, 50 different scenarios that you're running. I need to operate under each condition. I need to do analysis for each one. And there thus becomes this very thick report. It's because you have to document each and every one of these cases, right? Create a table for the client. In my opinion, I have to click on every condition, and EasyPower is in this regard because it instantly puts the VTHD on the bus, and I can identify the problem right away. I can also impedance scan and click the one line, open the tie, close the tie, open the main, close the main, go min, max, and average source impedance, right, on the source, and I can look at the impedance at every time, and then I can quickly evaluate which conditions I'm worried about, document that one case, and say all the others are good. So I can take a study that would take somebody weeks to tabulate and evaluate real quick. And that's the one I showed the client, the one that causes the problem. This is the concern, and for this reason, you have to buy a filter, right? And that's really the only one that matters, is if it's an operating condition that causes a problem, that dictates that you need a filter, you gotta go buy a filter. So again, that red reference line there is pretty important. You can see that we've significantly increased the impedances of the network from the base value of the transformer. Effective short circuit impedance, we talked about this. You got this varying frequency, this varying source impedance here. That's going to shift your resonance. The capacitor bank can also come in at 0 plus 10%, right? So do your analysis, and you're going to make an assumption, but the value you get from ABB or Cooper or GE or NEPSI, I guess, and will be some value, right? But it's going to be 0 plus 10 because that's what the IEEE standard says, 0 plus 10. They're testing to that. For your information, generally it's about 0 plus 2. They're pretty exact. The manufacturers can hit it pretty good. But the standards say 0 plus 10. You have a motor impedance. As you turn on the motor impedance, the subtransient reactance of the motor acts to increase short circuit impedance, right? Acts to increase short circuit current, decrease short circuit impedance, let me say that right. And that's also shifting the curve a little bit, only maybe 0.1, 0.2. But if you're trying to do this thing where you're avoiding resonance and tweaking around it, you have to know things move around. When you do the analysis, a lot of times you want to look at VTHD on the bus. And your resonance could be shifted away from the fifth harmonic, away from the key harmonic, right? One of these principal harmonics. It could be away from that, and your VTHD table will look good. You will look at your table, everything looks good. But if you were to take a look at the impedance scan and you saw an impedance of 5.59, a resonance at 5.59, you should flag that, saying, well, that doesn't look right. We got to be concerned about that. I know my analysis that the table says is good, but when you look at the impedance scan, you should be saying, if I were to shift the impedance curve, if I were to shift this to the left a little bit, it's going to have the same shape. It's just going to slide to the left. If it goes over the fifth, I got. So you should be able to look at the impedance curve. And that's really what you want to do with these impedance scans is look to see if it corresponds to key harmonics, but then also think about if I shift a little bit to the left or a little bit to the right because things aren't exactly the way I modeled, do I have a problem? If you do, you got to do something. So we're on to this, current amplification. So what I did is I inject 1 amp in the model, and I say, what is my corresponding current, what is my corresponding current right here? Basically right here. I injected 1 amp over here, and I say, what is my current flow in the capacitor or what is my current flow here. So remember, I have 1 amp of current injection here, comes around, and then it hits this resonant circuit, basically, is what we're doing. And I'm saying, well, what is that current? And you can see that the current amplification at resonance can be, in this case, 80 times. 80 times the value that your drive is putting out. So I got a drive that only puts out 1 amp because it's a high pulse number drive. But if it's putting out 1 amp, it becomes 80 in the capacitor bank. It becomes very significant in the capacitor bank and also in the source impedance, right? Source impedance over here. So it becomes 80 times here, which makes you fail 519. You failed 519 then. So you have a drive supplier who says, I'm 519 compliant, right? You're not, technically speaking, the system's not 519 compliant. The drive might be 519 compliant, but you add a capacitor to the network is not 519 compliant anymore because you just multiplied that 1 amp, that 1 little amp by a value of 80 times, and that becomes a problem, that 80 times amplification. So if you're the drive supplier and you've got the blinders on, you're not looking at the network as a whole, the drive is compliant, but the system is not. And really, for system designers, they have to be looking at the entire system, which includes the capacitors of the network, the cable capacitance, all the drives. You have to look at the whole system as a whole. So current amplification is a problem. The red represents all the frequencies by which the current has gone up because I added a capacitor to the network. If you're taking harmonic measurements, I talked about this today. If you're taking harmonic measurements and you are measuring at this point here, which would represent the secondary main, a very common location to take harmonic measurements, secondary main. You want to know what's going through the main transformer. If you have a capacitor bank on right at this location, okay, at this location and you're measuring at the main, your current is being amplified. So the measurements become useless. If you want to take measurements to quantify this value here, to put into your model, have an existing system, I'm trying to create an impedance harmonic model, and I need to put a value of current in there. If you send some measurement guy out to take those measurements, he has to take the capacitor bank off here. If you don't take it off, the measurements here are a waste. They really are. You can't use them in your harmonic analysis. All you can do is say, yeah, I got some amplification, but the value of current will become less meaningful. So something to note. You have to shut capacitor banks off during measurements if you're going on the main. So adding capacitors as a 4.7 tuned harmonic filter. So what we've done is we've added this reactor, okay? And so we had the same capacitor bank. The capacitor bank changes a little bit. We have to bump the voltage up because when we put a reactor in front of it, we get a voltage rise at this point because it's negative. This is negative J, this is positive J. So the result is I need to add voltage to the capacitor, right? Because I'm going to have a 60 hertz voltage rise. So at the fifth harmonic, it's about 5%, 4%. It's 1 over or n squared over n squared minus 1 is the formula for the voltage rise on the capacitor. N squared, our tuning point, divided by n squared minus 1. So a fifth harmonic would be 25 divided by 24. That's the per unit voltage on the capacitor. So about a 5% rise is what you get at that point. So you have to put a higher voltage rated capacitor in harmonic filters. The other thing is as the filter draws harmonic current in here, okay, you're going to have the harmonic current, the value of amps times x of c, right? And you're going to get a voltage rise at each one of those harmonics. And those peaks will all have to be added together, and you have to make sure that the harmonic filter, okay, the capacitor rating, is above that value. So as part of having a spreadsheet tool, is if you have the spreadsheet tool, you can do a filter design, really, if you know what you're doing in 5 minutes. You can do a whole filter design. and you're putting in the values of current. And then you take that and you put it into your model, right? And it's that simple. So that part of it is very easy once you do it once. So when we put this filter in, we get this magenta impedance curve. And here at the 4.7, that's a 4.7 tuned harmonic filter, the impedance, okay, looking from here goes very low. So the 4.7 tuned filter, you have a very low impedance at that point. What's interesting to note is the magenta curve beats the transformer base impedance curve by a little bit at all frequencies above its tuning point. It actually reduces the voltage distortion in the plant for all frequencies above the tuning point. So a fifth filter will pull in 7th, 11th, 13th, 17th harmonics, and it's based upon an impedance divider. What is the impedance of this filter at a frequency versus the impedance of this, right? The filter is slightly more attractive because it's slightly lower impedance than that, and therefore it will take in current. So just because you're putting in the fifth doesn't mean it's not going to filter 7th, 11th, 13th harmonics. I bring up another point. If I were to tune this to, picture this, detuned cap bank, I just shift everything to the left and call it a detuned cap bank. What have I really done? I just moved this impedance point here, which is that value, and I just shifted everything left. How much did I really change that slope of the curve by sliding it back? So detuned banks really don't have a significant difference, 4.7 versus 4.2, not a huge difference. There's this notion that if I put in a 4.2 filter, it's not going to take any fifth harmonic current in. That's just a false statement. It's a false statement. If I were to take this filter and tune straight to the fifth, you would take in almost all the harmonic current because X of C equals X of L right at the fifth harmonic, and the only resistance I have is R. And the R of an iron core reactor is 100. X over R of an iron core reactor is 1 over 100. So very, very low value of resistance. Capacitor is 0.05 watts per kVAR. So very low resistance. So if you tune a filter right to the fifth, I can basically take in almost all the harmonic current that a drive can put out. And that's common. When I can't meet 519 because I tuned it at 4.7, I would tune straight to 5. So it's not a rule that you have to hit 4.7. You see it all the time. Manufacturers are saying 4.7, 6.7, right, 10.7, and you do that. And the reason they're doing that is because they don't want to take in all the harmonic current because we're taking a chance to take in all that harmonic current. If I take in all the harmonic current of the network, that reactor right there has to be able to handle all the current risk. But if you have a customer who will say, I don't want to buy all that reactive power, I want a smaller bank, right? And because it's a smaller bank, I might want to try to filter more current, right? So you have to make sure, right, that the value of your tuning point and how much current you're taking in, okay, is within the range of that reactor. So something to consider. And then, of course, you have the tolerances of the reactor and the capacitor. The reactor is going to be plus minus, maybe 3, maybe 5%. In the capacitors, 0 plus 7, 0 plus 10. So you have this tuning point that shifts around. So a lot of times you specify taps on the reactor because I want to be able to move it a little bit. You might tune to, okay, another point I think I'll make here is say my tolerances could be that it shifts this point here, shifts it up, right? So I take this, let me get here. If I shift this point up to say 5.1, you get this resonance right here will shift to the right, right? This resonance shifts to the right over the fifth. And that's one of the reasons why we tune to 4.7, is because if I have a variation in my tuning point and it shifts upward, I don't want this resonance right here to cause a problem. All right, that's the issue. I want to make sure that doesn't cause a problem. So you tune below. But sometimes for your analysis, you need to filter every bit of amps you can And you do that by tuning straight on the frequency. Another thing, and sometimes I will design the filter so it's tuned above the harmonic. And especially in the multi-tuned filters, the slope of the impedance curve might come down, but then come up fast. And if it comes down slow, it comes up fast, I'm better off to tune above because a small variation is a small change in my impedance of the filter. So it's not always the case that you design your filter to be tuned below frequency. Sometimes you go above. So I put a couple of slides in here for the Bechtel people because I was here today and I wanted to change it up a little bit. So in this case, I'm showing physically a harmonic filter. And in this case, it's just a single phase. I got the source coming in. This is basically the line terminal. Goes through an iron core reactor, is typical, comes out and goes into a capacitor. So I'm kind of showing you the difference here is we've added a reactor. That reactor is 1/25th. If it's a fifth harmonic filter, it's 1/25th. You've only taken away a little bit of the megavars, right? It doesn't add or change a lot. The filter bank is acting as a capacitor bank, so it's still putting out reactive power. Okay.
What was the cost to go up so significantly?
It's that reactor. The reactor costs money. And I'm going to show you why, because of that. It can be expensive. Now that's a very big reactor, but you can see it represents cost. That's a single phase iron core reactor. This happens to be the largest filter reactor that we've ever purchased, but it's big. All right, and so typically like a 15 megavar reactor would be not quite so tall, but on that order of magnitude, you're starting to get up there. So it can be very heavy. There's a lot of weight there, and that's just one phase of a harmonic filter. You still have the other two phases, and if it's a multi-stage bank, say 30 megavars, and you have three 10 megavar banks, you're adding in these iron core reactors on every phase, and you're wiring those in. So that's the cost. The capacitors haven't really changed, right? Not that much, just a little bit. The reactors is where the cost is. So very, very expensive device. And if not properly designed, will be a major headache. So we have a design philosophy that is to overrate those reactors, because when they are not designed properly, they throw out a ton of heat, and they vibrate, they make a lot of noise. So we have a philosophy that the fundamental current rating of the bank, we take that reactor and we multiply by 1.5, the current. So if if the bank, the X of C, X of L, you take those two values, you calculate the kVAR output, and you calculate a nominal value for the filter bank of 100 amps at the fundamental, we will ask our supplier of the reactor, we want 150, which is a lot, but we're operating then at about 50% of its losses and 50% of the forces inside the reactor, so the thing will just sit there and be quiet. And then the harmonic value, we go by either 50% or 100% rating on the reactor. So what I mean by 50%, it means that a fifth harmonic, I would rate at 50% of the fundamental or 100% of the fundamental. The reason we do that is even if the study only shows 10 or 20 amps, I'm still going to want 100 amps, because the study doesn't always come out to be exactly what you get. You might have not been told about some large drive. In the future, the customer might add a large drive, so you want to add rating in the reactor. And if you don't do it, the thing will run hot, it will vibrate, and it will become a problem. So just put money in it. You're not paying a lot for that extra cost. You've already paid for the reactor, you paid for the guy to design it and ship it, so why not add 50% margin? It comes in at a fraction of the cost of the reactor, a real fraction. So the number one problem with harmonic filters is underspecified reactors, whether it's air core or iron core, underspecified. In other words, underrated. Somebody did not put enough rating in the design, and you're not paying much for that extra rating. So for us, if you add reactor rating, we sleep at night. I don't have to deal with phone calls on Saturday saying I'm tripping on thermal overload, or the thing is loud, or it's failed, or there's stuff dripping out from underneath. These are the things that I have dealt with the last 20 years. So now I just say, do it our way, or go buy the cheap thing and pay for it later, right? And that's really the difference. And if you're going into an expensive process plant, a mine, they don't want to shut down. They do not want to shut down, and they get very mad if their filter does not run, because a lot of times the process will not run if the filter does not run. So you have to have reliability in the design, because a filter system that's down might represent the whole process being down. And now you're talking about hundreds of thousands of dollars per hour, per day, right? So for the cost for some margin in the design. So that's my lesson on that. So open rack, filter bank, metal enclosed filter bank, air core reactors here, right? So you have air core reactors here. You have capacitors here, right, in a rack. And here you have resistors. So it's a open rack arrangement. We don't build these. This is the same, is an equivalent filter bank in a metal enclosed version, but it's a two-stage filter bank on the right, metal enclosed, two-stage on the left. That's what I call an open air solution. This was made by a company called PhaseCo. You guys ever hear of PhaseCo? They were very popular 15 years ago, 10 years ago. The guy passed away, the owner, but he was a competitor here in Texas. And anyways, that's his picture. I found it on a website, but he is long, I think, passed. So question 4, what are the key benefits to adding capacitors as a harmonic filter? And I say the key answer here is you, A, avoid resonance. It's one of the primary reasons to add a capacitor as a harmonic filter is to avoid resonance, prevent resonance. Okay, if I tune a bank to the 5th harmonic, that means I cannot have resonance at the 5th. I will not have it because I've precluded resonance because I tuned the filter there. So oftentimes I want to prevent resonance at the 5th, 7th, 11th. I put a filter at 5th, 7th, 11th. And this is something that sometimes you have to do. You want to prevent resonance. So that's one of the key benefits of adding capacitors as harmonic filters. The other one is if you need to filter, then you need to add a filter, right? So you add the capacitors as filters.